Good morning, good afternoon, and good evening. Thank you for joining us today. My name is Maureen Price, and I will be the moderator for our presentation. I am the leader for Fluor's Business Transformation and Innovation team. We focus on new and innovative ideas, never losing sight of the critical thinking and analysis that comes from our global team of expert engineers and designers. Our people are at the core of our success. Every one of the Innovation Builders team and the speakers on this call are remote working parents and grandparents, and we applaud their ability to find the time to share their knowledge in addition to serving their clients while juggling the intersection of their career and home lives. As with our other webinars, this will be a technical presentation intended for anyone who is interested in hearing about the latest and greatest in REAC corrosion. Everyone from mechanical and process engineers to inspection experts to reliability to operations staff. We will cover the current state of the art of this important topic. At Fluor, safety is our #1 priority. So normally we start every event with a safety topic. However, since our topic today is essentially an hour-long safety and design topic unto itself, we will omit a separate safety topic. Our speaker today is Cathleen Shargay. Kathy is a Fluor Senior Fellow with specialty expertise in material selection, corrosion, and welding. She specializes in these areas, specifically material selection and fabrication, corrosion, and welding. Her experience includes failure analysis, technical consulting, specification development, production of corrosion control documents, and practical field support. She is very active in both NACE and API and has received the NACE Technical Achievement Award. If that isn't enough, Kathy is also an avid marathon runner and skier.
Thank you, Maureen. Welcome, everyone, and I hope that you find this talk informative and beneficial. So I'm going to be speaking on the latest and greatest in reactor effluent air cooler corrosion. This is one corrosion problem that the industry hasn't completely solved, and API and NACE have been issuing documents, and we have many committees, and we have guidelines, but we're constantly trying to improve the guidelines. So for this talk, I'll go through a description of the corrosion locations in the hydroprocessing units. I'll give background on ammonia bisulfide and ammonium chloride corrosion mechanisms. I will describe API recommended practice 932B, and then we'll go through a literature survey we recently were able to conduct. We'll go through the results and then overall conclusions. And one kind of side topic, but I didn't want to leave it out, is the latest on the use of duplex stainless steels for the reactor effluent air coolers. Okay, so what is a REAC system? So the reactor effluent air coolers are in, the ones we're speaking of are in hydroprocessing units. And these units in refineries are used to take heavier hydrocarbon feeds that come from, say, the crude unit or FCC or coker, and crack them into lighter, more valuable products such as gasoline. Or the units may be removing contaminants from products. They would be removing sulfur, nitrogen, etc., in order to meet the gasoline or other product specs, and some units accomplish both. The units always have a reactor operating at very high temperature and high pressure, and it has injected hydrogen in order for the chemical reactions to take place. These units contribute significantly to the profitability of most refineries. And then the REAC, the reactor effluent air cooler, is an air cooler cooling the effluent stream as shown in the following schematic process flow diagram. So this is a typical PFD of a hydroprocessing unit, but there are many options. And you can see the feed coming in at the lower left goes through some feed effluent exchangers to be heated through the feed heater, fired heater, and then to the reactor with the hydrogen also being injected there. Then you have the reactor effluent. It comes out and is cooled through some shell and tube exchangers. And then we get to the REAC area. So by the REAC system, we're talking about from the upstream exchanger through the water wash injection point, and that water wash is one of the key steps of the corrosion control, to the air cooler itself, to the outlet piping, and even the separator. So that's the entire what we're calling the REAC system that can be susceptible to some of the corrosion mechanisms we'll be discussing. Okay, here's another variation of the units. In this unit, the one difference from the previous one is that the reactor effluent now has a hot separator. So after a bit of cooling through shell and tube exchangers, the hot separator might be at about 500 F or so, and that separates out any condensed hydrocarbons, which go out the bottom, versus the vapors, which go out the top. This affects the corrosion in the REAC because now you don't have the beneficial effects of having some liquid hydrocarbon there, which kind of act like a coating on the metal surfaces, because the corrosion is occurring primarily where water is in contact with the metal surfaces. So now that it's only vapor, the corrosion mechanisms have a higher risk of occurring. And it makes the water washing a bit more complicated and so on. But the hot separators provide a lot of process benefits. So that is the trend that more and more units use the hot separators. But otherwise, the mechanisms and the corrosion control steps are very similar between these different units. Okay, so we'll go into the details on the corrosion mechanisms. First, we're going to do ammonia bisulfide corrosion, and then after we'll do ammonium chloride corrosion. So ammonium bisulfide corrosion is a high pH aqueous corrosion mechanism. And that's unique because a lot of in the corrosion engineers world, most corrosion mechanisms occur at lower pHs, but this is one unique one that occurs at high pH. It has many variables that you need to review in order to know where it's going to occur, what the corrosion rates are going to be. The variables include the ammonia bisulfide concentration, H2S partial pressure, the velocity and flow regime. They combine to give you something called the wall shear stress. That's really the key variable that we track for determining the corrosion risk. Temperature, that water-oil ratio, then the presence of any other corrosives that might be there, like cyanides or oxygen, which both of those would greatly accelerate any predicted corrosion rates. With all these different variables, it is very difficult to predict the locations and the rates without using a software. So the industry about 18, 20 years ago formed a joint industry-sponsored research project, which Fluor was a member, and we did thousands of lab tests, bracketing all those different variables, and it did generate a very useful software tool called Predict SW. So using that software tool now, we feel is a much better tool for predicting where corrosion will and will not occur. One typical rule of thumb is that if you're below about 1% ammonia bisulfide concentrations, generally the risk is very low. So this is a corrosion mechanism that typically occurs in the aqueous phase. Since this is a multi-phase flow with liquid hydrocarbon, hydrocarbon vapor, and water, the flow is very non-homogeneous. Things are swirling and hitting different surfaces in different manners. And often it's wherever the water is particularly touched, swirling against the metal surface, that's where the corrosion occurs. And the corrosion will look like a general washout, especially, for example, one of the failures was on the outer bend of an elbow, and it blew out such an area of thinning, maybe 10 inches long by a few inches wide, that when it ruptured, it looked like, the corrosion pattern looked like a football. It can also manifest as under deposit corrosion, but this is far less common in the hydroprocessing units, as the ammonia bisulfide deposition temperature is normally below the water dew point. So there's already water present, even if you're upstream of there's already water present. So if deposits were to possibly form, they are often washed away. But the number one way we avoid ammonia bisulfide corrosion, if it is predicted to occur on carbon steels, is by upgrading materials. So the order of upgrading materials would be from carbon steels. 300 series stainless steels have a much improved ammonia bisulfide resistance, but they're still rarely used due to the risk of chloride stress corrosion cracking. Another mechanism that can occur. Now, duplex stainless steels have been widely used and are definitely excellent for resisting pretty severe conditions of ammonia bisulfide corrosion. But again, another problem started occurring. There's been, and we'll talk more about this later, but there's been a number of failures at welds due to a hydrogen stress cracking problem. So I have more slides on this at the very end of the talk. So now one of the most common upgrades when you think carbon steel is going to corrode is alloy 825. And if it's in very severe conditions, you might go to alloy 625 or Hastelloy C276. And even going from carbon steel to 825 is a major increase in cost. Just material costs are probably 5 times higher. So the first step, if you feel you're going to have a risk of corrosion, is the material selection. And then if you're staying with carbon steels, especially, but even with cases where you've upgraded the air cooler, because you might still have some carbon steel piping where you have the carbon steel separator, it's still very important to implement the other corrosion control steps. So the water wash, remember we saw the water being injected upstream of the reactor effluent air cooler in those PFDs. So water wash is a key step for preventing this corrosion. It both avoids deposits and it dilutes the ammonium bisulfite concentration. And there's many guidelines to achieve a proper water wash. You have to have the right quality of water, can't have contamination with oxygen or cyanides. It needs to be injected with spray nozzles to make sure it has very good distribution. Often there's a debate on whether to have a single water wash injection point far upstream of the air cooler, or to have individual injections at each inlet to the air cooler. And some units, the best thing to do is use both. And Fluor's published a paper on a decision-making process to determine if a unit is best with single, multiple, or both. The piping and the REAC have a lot of design guidelines. Especially the inlet piping is often required to be what we call balanced, so that each flow split is just splitting into a T, not trying to do a header with a bunch of different branches coming off. Because you can see if you do that, you're going to have differences in flow inhomogeneity and differences in velocities. So piping has a lot of design guidelines. The REAC itself has design guidelines, like we usually require just either one row in the inlet pass or max 2 rows, because if you start having more rows in your inlet pass, again, the water distribution in the REAC is mainly going to only the bottom row of tubes in that inlet pass. So if you had more rows, the top rows could be starved of water. We have velocity limits, mainly to try to stay in the acceptable flow regimes. We set limits on lots of process variables, temperatures, the water quality, things like that. And in order to make sure that the unit doesn't change over time, and because these variables are still within design conditions, so in order to make sure it just doesn't change by process creep, we call that, we set integrity operating windows. There's actually an API standard on this, and the industry has adopted the acronym called IOWs. So it's important to set many IOWs around the REACs in order to keep a monitor of the variables that can affect the corrosion. And then the inspection programs. If any systems that have carbon steel in the area of the REACs, just about everyone has way more inspection thickness monitoring locations and does the inspections much more frequently than other systems, just since there is a risk of corrosion and you want to even try to detect any onset of corrosion before it gets significant. So you can see that this is a very important mechanism for the industry, and that's why there's some very good industry standards on it. So this is a good break point.
Thanks, Kathy. We've had a couple of questions come in, and I'll go through them quickly. Can you describe the appearance, the color and texture of ammonium bisulfide corrosion?
Okay, yeah, I mentioned that it looks like a washout. So the metal probably won't have any scale on it at all. It'll be fairly clean metal, and just a gradual thinning from the area that's full thickness down to the worst point into the center, a very thinned, washed out area. So no colors and no real corrosion products are forming there.
Okay, great. Here's a follow-on question. Can inhibitors be used to reduce the risk of this ammonium bisulfide corrosion?
Okay, yes, and especially if there's a risk of cyanides being present. So some plants inject ammonium polysulfide, which has the benefits of if there's cyanides present, it kind of neutralizes the cyanides, and it helps form a more tenacious iron sulfide scale that also helps reduce corrosion. So some units inject APS, usually with the wash water. And then there are some units that have used filming amines, but filming amines, it's tough to have them protect those high velocity turbulent areas. The turbulence washes away the films too. So they're not, they can't be considered fail safe and your only form of corrosion control, but they might be beneficial overall. But not too many units are using the filming amines, just a few.
Okay, thanks. So a whole bunch of questions are coming in. I'm going to give you one more, and then we'll leave the rest of them for the end. But on the selected software, you mentioned Predict SW. Does the selected software affect the quality of the corrosion assessment? Are there alternatives? Is there anything else that you know of instead of Predict SW?
No, I don't. It's in the corrosion engineers world, there's numbers of different software packages, and many of them are just for very unique environments. Like there's other softwares that are for when you have H2S and CO2 present. But the only one I know of that does corrosion for when you have H2S and ammonia present, and then even considers cyanides and things like that, the only one I know is Predict SW.
All right, great. Thank you so much, Kathy. Let's move on to the next portion of your talk, and we'll queue up the rest of the questions for the end. And to all of the attendees, please continue to submit your questions to all panelists. Thank you.
Okay, so now we're going to switch to talking about the background on ammonium chloride corrosion in reacts. If chlorides are present in the reactor effluent, one of the risks is that ammonium chloride deposition temperatures are often high above the water dew point. And when we're saying chlorides are present, even 3 ppm of chlorides can be enough to start getting us into troubles. And we show a deposition chart on the next slide. Now, for units that are having the ammonium chloride salts, and sometimes they're occurring upstream of the water injection point, say in that last shell and tube exchanger, feed effluent exchanger or reactor effluent stripper feed exchanger, if you're forming the salts and they're dry, they're not going to be corrosive because it's still an aqueous corrosion mechanism. But the dry salts can lead to pressure drops, and some units have to do an intermittent water wash every month or something like that to wash away the deposits just to get rid of the pressure drops. But the thing is, if the deposits are wet, and by wet, it doesn't even mean that you got to be below the water dew point, because the deposits themselves are hygroscopic and can absorb moisture just within the deposit. So there's not a bulk water phase, but the deposit itself can be what we're calling wet. If you get wet ammonium chloride deposits, the corrosion rates are extremely high. There's definitely case histories of leaks that have occurred in days and then some in weeks. So they can't be managed, and a lot of times it's very difficult to even know the corrosion is initiated until you have a leak. So that's the main corrosion risk with ammonium chlorides. It's whenever you can have a risk of forming wet deposits. Actually, once the ammonium chloride is in the water phase, the concentrations are always far too low for that water phase to be significant corrosion of ammonium chloride. So here's the deposition curves. They're from API 932B. We redrew them. So the x-axis is temperature. The y-axis is a product of the partial pressure of ammonia times the partial pressure of the acid species, the chlorides, the bisulfide, and it even has curves for fluorides and bromides. And this allows you to see, if a given unit would say 3 ppm of chlorides and then the ammonia, where the ammonium chloride deposition temperature would be. So and then you might be saying, well, gosh, how do I know if my ammonium chloride deposits will be wet or not? So once especially Fluor trying to design new units or doing a revamp, we will determine the predicted deposition temperature, and then there are calculation methods for determining if they'll be wet. Fluor actually published one paper on this, and then a few other papers have been published since that even refine the methods further. But Fluor's practice is to not allow any predicted ammonium chloride deposition in our new designs of new units, wet or dry, because we feel that there's a risk of, first, there's always multiple design conditions for a given unit. So we have the start of run, the end of run, then we have turn down conditions. So within all those design conditions, there's usually one that might mean that these deposits are wet. And then we also feel there's such a high risk of the process conditions changing with time. So we feel that even if initially the designs show that the deposits should be dry, at some point there's some risk that they'll be wet for changing feeds, for changing flow rates, for some reason. So Fluor is very hesitant to design any unit with any kind of risk of ammonium chloride deposits. And another reason we don't want to risk these deposits is there's no fully resistant material to wet ammonium chloride deposits. So it's not like we can say, oh yeah, there's a risk in the shell and tube exchanger, let's just upgrade the alloy. There's just, even if you put in the best materials like alloy 625 or Hastelloy C, if it forms wet ammonium chloride deposits, there's cases where they've still had leaks. So if a unit will potentially see chlorides in the effluent, our steps are, first we will try to determine the source of these chlorides. The chlorides can either be from the feed or the makeup hydrogen, and we can study ways to possibly remove them. So if the chlorides are coming in with the feed to the hydroprocessing unit, it might be that the crude unit could improve the desalting or somehow just remove more chlorides from this feed source. And or if it's the makeup hydrogen, which could be coming from a CAT reformer unit, maybe we can add a better absorber in the CAT reformer unit so that the makeup hydrogen doesn't have the risk of chlorides coming to the hydroprocessing unit. So that's one of the first steps that's done. The second step that's looked at is, can we add a continuous water wash upstream of the ammonium chloride deposition temperature? But this is often tricky too, because that could be a very high temperature, because say it's the deposition would occur in that last shell and tube exchanger on the process flow diagram. Now you got to put the water wash upstream of that, and that's going to be quite a high temperature. It would require a huge volume of water, might be difficult to get a good distribution. So that's often very complicated. And then another option is to set an IOW on the minimum temperature. So say we're worried about that last shell and tube exchanger, maybe we design that exchanger or have a bypass around it on the other side so that the effluent stays at a minimum temperature at the outlet of it so that it's staying still above the ammonium chloride deposition temperature. This is sometimes works if you're kind of borderline on the very close to the deposition temperature, but and this will ensure you do stay above it. But if you're far above the deposition, if you're far below the deposition temperatures, this just wouldn't be achievable or practical. So if there are units that still have a risk of the ammonium chloride deposits, one of our steps is we do realize you got to have the water wash upstream of the ammonium chloride deposition temperature plus the safety margin. And then to help remove all the chlorides from the vapor phase, we've found that any use of spray nozzles, we couldn't get there. Even the best quality spray nozzles, the finest droplet sizes, they still coalesce too quickly to really say that we've effectively stripped the chlorides out of the vapor phase. So now we've seen that a number of units, and Fluor's done a bunch now, where we have the static mixer right after the water injection point. So the static mixer enhances the contacting of the free water with the effluent, improving the absorption of chlorides from the vapor phase. Otherwise, even downstream of the water wash, any place there's a vapor phase, like stratified flow and horizontal piping, in the REAC tubes that might be stratified flow, that vapor phase still would have a risk of forming ammonium chloride deposits if you don't strip the chlorides fully out of the vapor. So static mixers is kind of one of the innovations not innovations, but the latest and greatest practices that we want to highlight in this talk. Okay, I do want to mention API RP 932B. Its title is Design, Materials, Fabrication, Operation, and Inspection Guidelines for Corrosion Control in Hydroprocessing Reactor Effluent Systems. Its third edition was just issued, June of 2019. Its previous first and second editions were 2004 and 2012. It's 60 pages. I've been very active on this committee throughout these different editions. I would call this document as very thorough on all aspects of preventing ammonium bisulfite corrosion. It's an excellent industry summary. But the design, monitoring, controls, etc., to prevent ammonium chloride deposits is limited to about 2 pages. And I think this is because, the industry hadn't focused on ammonium chloride in the past. It's and the guidelines for fully removing chlorides from the vapor phase and preventing this corrosion just aren't fully determined yet. The industry is still working on this. Fluor's written some papers and others too, but the experience and guidelines are still evolving. Okay, so let's go through one example. So what you're looking at here is the tube layout drawing for a reactor effluent air cooler in a hydroprocessing unit. But this air cooler had 5 rows in the inlet pass, and every black tube that you see there is one that had a tube leak. So you can see those, the 5th row did fine, and that's the bottom row of the inlet pass, no leaks there, but going upward, 4th, 3rd, 2nd, 1st, more and more leaks. So the inlet nozzle is at about the center of the bundle, and you can see that the worst leaks are in the far upper corners where the water would have a very tough time reaching those corners. So the water by gravity just goes to that bottom row in the inlet pass. So here's one of the tubes with a leak. So the tube was removed, and now it's been sectioned right through the 3 and 9 o'clock positions, and we're looking right at the top of the internal surface of the tube. And you can see it had a heavy deposit, and the headers of this air cooler also had heavy deposits. In a lot of areas, the deposits were very white, but you can see this looks black because there's also hydrocarbon that kind of is on the outer surface of the deposits. So this is what it looked like after those deposits were removed. Oh, and so this is the classic appearance of ammonium chloride corrosion. Because it's a corrosion under wet deposits, it's often very pitted looking. And you can see some of these pits look like they're just about through wall, and this pitting is what led to all those tube leaks we saw in that first tube layout drawing. Okay, some additional important points about ammonium chloride corrosion. The deposits can form in horizontal piping, and it always forms in the top. So that's almost a key clue that it's ammonium chloride corrosion that's occurring, is when the corrosion is at the top of either piping or the tubing. So we can form deposits in the horizontal piping downstream of the water wash injection point if the flow is stratified and the chlorides have not been removed from the vapor phase. So they'll be at the top of the piping. And another warning is that even if your flow modeling has said that it's going to be annular flow, which sounds much better than stratified flow, sometimes annular flow is only a smile. It doesn't fully go around to merge at the top of the pipe, and so it's not wetting that top of the pipe. And in that case, you can still have these deposits form and lead to the corrosion. So at this point, many units with chlorides are adding the static mixers at the water injection points, just to help ensure that these horizontal runs and such don't have this risk downstream of the water injection point. And that unit where we looked at the failures, that was what was the solution for that unit. It eventually added a static mixer at the water injection point. And then most of these problems have been solved.